Assalamualaikum warahmatullahi wabarakatuh. Yeah, I cannot hear anyone. Okay, make sure everyone's signed in their attendance. Oh, thank you, Akmal. I'm gonna start recording so that I don't forget this as well. There's 14 of you here. We're expecting about, no, there's 13 of you here. We're expecting about 7 more, 8 more. Um, all right, make sure you head over to your classroom and be on standby with the project activity that on solid waste characterization, because we're going to discuss your group work. There are 11 submissions apparently, but I'm not sure why there are 11 submissions when there's only supposedly 21 divided by 2, 10. Yeah, okay, that makes sense. Bahagi 3. Should be only 7 or 8 groups. Did anyone make only a group of 2? Did I say pairs or groups of 3? May 3 orang kan? Let me just double check. Oh, there are some pairs as well. Did I say pairs? Maybe I said pairs. There are groups with 3 people and there are groups with 2 people. Excuse me. Never mind. We're here to discuss your findings. So I'm going to share my screen. Okay. All right. Let's see your answers. So what we did was try to understand or investigate some of the commonly measured properties, physical and chemical, of solid waste. And I'm going to ask each one of you to, well, some of you to present your findings. Putri Nur Hidayah is the uploaded. Nurjana, can you please tell the class what you found about particle size distribution? Nurjana, are you here? If you're not here, maybe one of your group members can help. Okay. Try again.
Kenapa boleh jadi macam tu? We might on lagi lah.
I am very happy that you're all very excited to be during class, to be in the class. Okay, when you're ready, Jana.
Doctor, I need to present the Excel or
You can just type it in the chat box. Come on. Uh, okay.
with
I think they are all together in one room. Some of you guys need to turn off the mic.
Okay, the next group will be Rohimatu Toyibah's group. So can you please be on standby?
okay. Everyone can hear me, right?
Yes.
Doctor, I just need to explain about the particle size and distribution, right?
Yes, correct.
Okay. Okay, so our finding in particle size distribution is for the typical for the unit, of course, it is in mm. So for the typical range for organic municipal waste, we obtain a range between 25 to 50. And for the inorganic municipal solid waste, we obtain 76 to 101 millimeter.
Okay. Carry on.
Okay. Okay. So the purpose for the particle size distribution is useful for material recovery, especially for the uh, mechanically useful, and it is the key role design in mechanical separator.
Okay.
Okay, so for the method of analysis is the sieve analysis by using the British standard of test sieve shaker.
Okay.
So
We
this
use
is the formula, but actually we did not go detail into this. We still do not understand on how to apply the formula.
okay. Carry on.
Okay, so this is just same with what I say on the purpose of particle. That's all. This is just the reference.
Okay. What was your reference again?
Sorry, this one.
Okay. So the way the particle size distribution is done is very similar to how you've done your particle size distribution in your soil lab. I think you do have a soil lab where you conducted.
Yes.
Yes, doctor.
Yes, it's very similar, and it's just the difference is that instead of using soil, you're using solid waste and trying to classify how many percentage of certain size particles you have. And it is correct that this is particularly important for materials recovery because a lot of the technology used actually can differentiate your particle size, can separate your materials based on the particle sizes and the densities as well. The other thing is you also saw that there are ranges for inorganic and organic materials. I will show you a figure later where you can see that there is a distribution whereby glass sit around a certain narrower, smaller size particle range, and is plastic and paper is tend to be larger in particle sizes. Okay, next group. Rabiato Toibahan naman tadi. Siap.
Thank
Thank
you,
you.
doctor.
Thank you, Dana.
Okay, doctor.
And then the next group is going to talk about bulk density and material density both. So I'm gonna call upon who's next just now? Did I call? Ini ke? Is this group? This is the same group. Group Rahimata Toiba, Siti Liliana, and Nur Sabrina.
Yes, doctor. Okay, doctor.
Okay. Jana, you can stop sharing.
Sorry, doctor. Okay.
Next. There you go. Thank you.
Doctor, can you see my screen?
Yes.
Okay. So yeah. Okay. We have to present about material density and also bulk density.
Okay.
Okay.
You guys are very happy today. I wonder what's causing all of this excitement. Cannot
I
be the
don't
solid
know.
waste.
Okay. So for material density, so we found from the journal, we actually got 0.9 to 2.0. So actually, material density, what we found is the same as specific gravity. Okay, this one. Okay. So for specific gravity, there will be no unit for it because of the divisional factor. And then this one, the purpose of finding the material density is to determine the density of solid waste to prepare for volume of landfill required. Because it's actually the same as in bulk density. It's just that for bulk density, we are not considering the water, unit water. Okay.
Method of analysis.
Okay, for the method of analysis is that we're going to weight the fixed volume container, and then the the formula and the standards is referred from ASTM E1109-19. Okay, so this is actually referred from reference.
So is there a formula? I couldn't see.
Oh, the formula is not included. It's actually just the bulk density. We just have to divide it with the unit weight of water. This one. Okay, I will put this.
Okay.
The formula. I will put that.
Okay. I'm not sure about your description of material density. So can I ask another group to
Oh yeah,
maybe
sure.
to share what they found about their material density? So let me call upon. Okay, group Amira, Atikah, and Nurul Ashikin. Amira Atika Nurul Ashikin. So what did you find? Did you? So maybe you can help present what you found to be material density, because I don't quite agree with what they found.
Okay.
Mm.
Okay, for the material density, we found some. The unit of material density is from this is actually megagram per meter cube. This is the value that we get from our research. For the food waste is 1.0, for the garden waste 0.3, paper 0.4, 1.1 for plastic and rubber, 0.3 for textile, 0.45 for wood, 6 for metal, 2.9 for glass and ceramic, and 1.8 for ash, rock and soil.
Okay, Jaya, one comment is that your unit is kilogram per meter cube, but the typical ranges is not in the same unit. So you have to be more consistent there.
Yes, sorry.
And so I think I tend to agree with your material density definition here, but why is your bulk density also divided into materials? So just for the class, I think some of the other groups got this right. Bulk density is the entire solid waste without regarding what the materials inside is the entire bulk, the density of the entire bulk, whereas the material density is the if you divide the bulk into different materials, say paper, plastics, food, the wet portion, so the wood, contoh apa, textiles, then you can also come up with the density for each component of the bulk. So bulk density and material density, they are both density measurements. So density is just mass over volume, but the difference between bulk density and material density is that bulk considers the entire bulk, whereas materials considers different components. And the purpose for bulk density is as what you have indicated, but not necessarily just restricted to landfill disposal. So it's always for volume estimation. Typically used for volume estimation, but also you can think about sizing of trucks for waste collection. You need volumes for this as well. So any facilities that processes solid waste requiring some sizing will require the estimation of the bulk density of the landfill. So the the solid waste. So solid waste average bulk density is around 300 kilograms per meter cube. That's the range. But then once you send it to the landfill, it's going to get compressed multiple fold, then it will be almost 2.5 times or 3 times higher in terms of the density. So that's my comment. So bulk density is mass over volume. The way you measure it is just measuring the mass, dividing it over the volume of the container. And it is including the moisture content of the solid waste. Any other groups wants to share their finding that might be different from what the two groups have presented? Tak ada, we move on to the next group. Who do I have open? Kavian's group. Kavian, are you by yourself here? Where's your name? Kavian.
I'm here, doctor.
Okay, Kavian, Navin, and Moaz, can you present to the class about field capacity? So take notes. Make sure you make corrections in your own spreadsheets as you're looking at your friends' answers as well. Okay, go ahead, Kavian.
So for fill capacity, based on what I found out is that the unit for fill capacity is liter per kilogram. I couldn't find any typical range for fill capacity. For the use and purpose, normally is being used in the management of solid waste where fill capacity is significant because it represents the amount of water likely to be retained by the solid waste prior to the production of leachate. Or for example, before the waste becomes saturated and water begins to flow out, forming the leachate. Uh, the method of analysis is fill capacity test with and without surcharge, and that's all that I found regarding fill capacity.
Liter per kilogram. So how many liters per kilogram of water? So you said you couldn't find any typical values. Did any other group found a typical value that you want to share? Thanks, Kavian. Anybody?
Thank you, Doctor.
Yeah. Yeah, any other groups found a value for fill capacity of solid waste in liter per kilogram? How many liters of potential water can a 1 kilogram of solid waste contain before it starts producing leachate? That's essentially what it means, roughly. Anybody? Let me look at other groups' answers. See.
Doctor, is that the unit is correct?
Some numbers are in percentage. Hold on, let me just double check. You are which group, Iskandar?
No, I'm wrong, Doctor. It's okay.
Oh
Iskandar
my.
can help.
Iskandar which group? Fazli, right? Must be dengan Fazli ni. Okay, kita Fazli.
Maybe Doctor can ask Fazli.
Okay, I will ask Fazli. Whenever I'm in trouble, I will ask Fazli. Oh, yours is in kilopascal. Kejap ya, let me check my notes as well.
Doctor, is it unit in percent?
Yeah, should be in percent. I think the capacity. Kejap.
And also the range between 50 to 60%, right?
I got that value as well. Cuma I don't have my reference textbook. I dapat kat isi my office. So I tak boleh nak confirm. So hold on ya. Let me check. Adik, where did you get that value from?
I got from the place.
There are references with liter per kilogram as well, and it's around it's about 1 kilometer. It's about 1 liter per kg lah, roughly, or 0.5 to 1 liter per kilogram if you're using that unit. But it is possible that there are multiple units to refer to the same thing.
Doctor,
Yeah.
our group got 0.2 until 1, in range 0.2 until 1.95 liter per kg.
Okay, so if you can also convert this, because this is liter per kg, liter is volume, and you can convert 1 liter to so liter per kg is kg of solid waste, liter in water, right? You can convert the liter in water to a kilogram as well. So if you convert that by multiplying with the density, then you get the top value in kilograms of water, then it can become a percentage. So it's both acceptable. So I think if you do a conversion between 1 liter per kg to a percentage, you probably get something similar like. Okay. Okay, moving on. Next group, I'm going to call upon to talk about. So basically, field capacity is primarily to do with landfill. When you're designing land disposal facilities, it is an estimation of how much solid waste can hold water before it starts no longer holding it. Okay, because this hole is primarily due to capillary pressure. Okay, next group is Fazli, because I've opened your group's slides. So Fazli, Akmal and Akmal. Akmal Arman and Akmal Arif. Can you talk to the class about permeability?
Hello, Assalamualaikum.
Alhamdulillah. What's the screen?
Okay, my name is Muhammad.
Hello.
Oh, share screen.
Uh-uh.
Wait. Uh, mana? Yeah. Oh. Can
Yes.
everyone see my screen?
Yes, we can.
Okay. So I will talk about the permeability. So it is measured in percentage. So the typical range is between 0 to 100%. So the purpose of the permeability is to measure the total amount of voids from the surface. And wait, so the method of analysis, the percentage ratio of volume of void, the percentage, it is measured by the percentage of ratio of volume of void to the total volume. So this is the formula for the porosity. That's all for porosity, doctor.
But you did not really talk about permeability. Tak apa. I may call another group. Nur Izzah. Let me open. Saya tengok dia punya result. This is full capacity. Porosity juga. Hold on. Permeability percent. Semua bagi persen. Yeah. Give me a second.
Doctor, we also in percent.
Let me refer to my notes kejap.
Okay.
I believe what you found in terms of percentage is just referring to porosity. Did any group found anything about permeability? Should be in time, distance over time. Boleh. Siapa tu? Fazli. So what does it refer to? So if porosity is the void over the entire volume, what is permeability? I mean, roughly, you don't have. It doesn't have to be formula. It can be something like what does it mean physically? You learn this is the same permeability as you would probably. Same like soil. It's just like now instead of thinking about soil, we're thinking about solid waste as the soil. Faham ke? Oh tu dia. Dynamic. It's just how much water, how much distance water travels through the material over time. It's just meter over second or meter over hour. So permeability is just a measure of how infiltrable is your solid waste. It is usually, yes, it depends on the particle size and also what kind of component is your material. So if you have a lot of more organics, it tends to hold more water. If you have a lot of, so if you're talking about soil, if some soils hold more water, and similarly some components of solid waste will hold more water than others. So if you have more organics, you will hold more water, therefore your permeability will be a bit reduced. Okay, and then this is also another parameter that is more relevant when you're designing landfills. You don't really use this parameter in the earlier stages of solid waste processing. So you don't really talk about it during collection. Collection is more about volume. In terms of, because you want to make, yeah, something like that, correct. So you have to make sure that you're not transporting leachate too fast, or you have to make sure that the it's about, correct. So we'll talk about landfills on its own later, but this is just for sort of generic introduction to what we measure about solid waste. Okay, thank you. So moving on, next group is going to talk about the more fun parts, I think, um of the analysis, which is proximate analysis. So how many groups do you have left? Who hasn't been called? Putri Nur Hidayah, have I called your group yet?
Yes.
Alamak.
Jana with Jana.
Nur Sabrina?
Yes,
Hamdan
I'm with
already.
Rohima.
Adik Hilman, can you talk to us about percent moisture? It's the easy one.
Sure, Doctor, sure.
Okay. Siti Zulaika, your percent moisture punya typical range salah ya. Tengok. Nanti check against Adib's results.
So
Hmm.
for the proximate analysis,
Zoom in, please.
Zoom. Alright.
On the proximate analysis, maybe you can cover percent moisture and percent VOC.
Huh?
Oh, tak. Satu je lah. Percent moisture. Nanti aku another percent.
Okay. Moisture only.
Moisture only.
So for the unit for moisture is percent in percentage. And also the range is around 65.72 to 65.80.
Okay.
And also
A bit narrow.
for the purpose is the moisture content at each material was measured through weight difference at 75 degree and how to it's okay lah. And the dry material was then grounded as using a solid waste. Wait, how to extend this one? Tak boleh lah. Yep.
Tak apa lah, just read. Okay, I think your percent moisture is very specific to the study that you referenced. So maybe they measured their sample and the range is very narrow. It's because their sample has only around 65% moisture, but solid waste, I mean, if you consider all of the solid waste in the world, it will be a lot wider than that. So can anybody share what they found instead? I mean, if I have to dig through all of the groups, macam susah. So maybe any one of you found a different typical range for percent moisture of
Okay.
solid waste?
I start sharing.
Okay, stop sharing. It's fine. Siapa yang saya taruh ni? Anissa?
Tak boleh.
Yes.
Saya kena buat public service reminder to make sure that you're muted before you say anything silly.
So I present about the percent moisture ke?
Betul Anissa. So if you want, you can share your screen.
Adib tak tutup mic lagi.
Oh, sorry.
You can choose
Oh, Anissa. Okay, yes. Anissa.
I'm the one with Juleka group.
Okay.
Yeah.
I think what your range of temperature ni is with the analysis itself. So how do you measure moisture in a sample? You heat it up higher than boiling temperature of water so that you evaporate all of the water. Then you measure the difference in weight that gets you the percent moisture. So that range that you have, that is the range of temperature to heat your sample, not the percent moisture itself. Dalam my notes from previous, I think the second week, ada rasanya range of percent moisture across solid waste management in different countries. So maybe refer to that and tengok balik. I think so it's quite a wide range. So if you have solid waste with a lot of food components, then you have a higher percent moisture. When you have it, when you have more, say, paper, then you compared to food waste, then you have less. Okay. So the purpose of so I muted you, Anissa. And so the purpose of measuring solid waste, percent moisture is to evaluate the potential of solid waste for incineration or versus other methods of treatment lah. Because if you want to incinerate, it is not really it might not be very economically feasible to incinerate solid waste with a high percentage of moisture, because you'll be spending a lot of energy burning the water. Also, if you are designing separation system, if you have a solid waste with a high percentage of of moisture, you'll find it hard to separate the different components, because all of it is going to be glued by the water. Okay, carry on. Which group have I not called? Semua group dah dipanggil ke? Rasa macam dah. Iskandar. Pandai Iskandar.
Dah lah.
Okay, I'll call Iskandar anyway. Because he hasn't talked today. So percent VOC, Iskandar, can you tell us?
Actually, we get the fixed one. We doesn't get the range.
That's okay.
VOC is volatilities, right?
Volatile organic compound.
Alright. So we get about can someone from my group share the screen? Iza or Nat? So we is actually used as the major quality measuring parameters that determines energy behaviors. So I don't know. For regulator's purpose to prevent the formations of ozone and constituents of photochemical smoke. I don't know whether it's true or not.
I think you're looking in the wrong literature ni, not solid waste. Not quite correct. So if we're thinking about solid waste, the percent carbon ni is volatile organic carbon is the percentage of carbon that you can volatilize. So that means you can burn it, and it can convert into gaseous form. So this is the percent carbon that you can quickly burn away inside your incineration.
Okay.
Okay. Tak apa, good effort. But I saw that some of your responses, not you, but some of everyone's responses, not very specific to solid waste. You just have to be careful that when you're looking at the different
Betul. It is because it is hard for us to find the percentage because each of the components of the garbage have different percent. So
But that's fine. I mean, the percentage is fine. That looks like a good average. Tapi macam your purpose ni, I'm commenting on the use ni.
okay.
I don't know. Well, it's not clear to me how it's relating to solid waste. It could be about the amount of gas that you're producing because volatile organic compounds tend to be containing very toxic, very components. But this looks like a more general air quality punya literature. But I'm not sure. You can double check.
All right. Sorry, Doctor. Thank you.
Don't apologize. Okay. Yes. VOC is very polluted. Okay. VOC is not very polluted. It's not very polluted. It's a pollutant. So basically, if your carbon can volatilize, is usually in the form of it's usually in the form of macam they will form compounds that are carcinogenic. So if you go to if you fill up your car with petrol, you smell gas, right? So what you're actually inhaling is a volatile organic compound like benzene, alkyl benzene. So they're not just one specific type. There's just a volatile organic compound is a kind of an umbrella definition for all carbons that can be in gaseous form. And because they can be in gaseous form and because they are structurally they form structures that can be toxic to your health, that is why they can be poisonous, and that's why they are called pollutants. Your cars also releases VOCs, and Iskandar is right when he said that it can contribute to the formation of photochemical smog, and that is true for air pollution. That's why if you operate in incineration, in incinerator, you have to treat the gas that you're producing inside your incineration system because otherwise you'll be releasing these toxic VOCs to the environment. And not only is directly toxic to human health, but it also can contribute to formation of smog because it will combine with nitrogen oxides and etc. So there. But the basically we saw what the proximate analysis was. I think all of you went through this, so I'm just gonna touch upon them. So you have when you do proximate analysis, you're measuring four main things. You're measuring percent moisture, you're measuring percent volatile organic carbon, you're measuring percent fixed carbon, and you're measuring percent ash. So this, if you think about it, if you're trying to burn your solid waste, there's going to the percent moisture represent the percent of the solid waste that is going to be vaporizing as water vapor. So all of this, if you are incinerating and also if you are recovering energy from incineration, you are not going to recover much energy because you're actually spending energy to just release water, to just heat the water and release it. And this VOC is the percent carbon that is easily burned. That means that it's going to be quick to actually convert this compounds that are in your this component of your solid waste into gaseous form. So they are the parts of your solid waste that is going to lose volume very quickly. Because when you burn, you're trying to reduce volume, right? And then your fixed carbon is also still, anything carbon is organic. So if it's organic, that means it can be burned. You can burn carbon, right? But fixed carbon tend to be kind of slow to burn. So if you have a high percentage of volatile organic carbon, you'll be reducing your volume quickly. If you have high percentage of fixed carbon, the process will take longer. And then the last part is your ash, percent ash. Percent ash is the residue of your incineration that is inorganic. That means it's not going to be able to be converted into energy. So you have to, this again, we're talking about solid waste characterization. We just want to have an idea about how our solid waste is, so that we can estimate how our plant or anything that we design is going to operate. So that approximate analysis. The other thing is there was the other part, which is the ultimate analysis. Ultimate analysis looks at more elemental components. Approximate analysis is more macam almost rough. Okay, what is percent carbon? What is percent volatile carbon? What is percent fixed carbon? How much is water? So it's kind of rough estimation of what your solid waste looks like. Whereas if you do ultimate analysis, you're looking at specific elements. So there are the first part. What was it called? There are two parts of this. One is major elements. Excuse me. And the second is trace element. So major elements is basically your C, N, CH, O, and S. Carbon, hydrogen, oxygen, nitrogen, sulfur, or sometimes you drop this oxygen, you don't really measure the oxygen. So you're measuring C, N, H, S. These are all the usually part of the organic components of your solid waste. You are actually measuring how much percentage of your solid waste is organic. And then you have the trace element, which are your heavy metals, very specifically looking at elements that exist in very, very small concentration, but even at small concentration, they can be very, very toxic. If, say, you produce leachate and you want to estimate how much is your final leachate going to be consisting of molybdenum, for example, or arsenic. If your solid waste has a high percentage of that element, then you may expect that in your leachate also there will be a high percentage of your. So it's about mass balance there. So that's kind of covers roughly what solid waste characterization. They are also, we might go back to some of this as we look at more design later. But that's just an introduction for you. It's part of the syllabus, so we're going to learn about them. The most important ones that for you to know, at least in the first half of the course, is your bulk density and your particle size distribution. So those are some of the ones that we are going to learn in the first half rather than in the second half of the course. So I hope you learned a bit from your investigation. You can look back and reassess whether or not what you found was correct. I'll also quickly look through your answers and comment on things that I find it could be very wrong. So if it's very wrong, I will comment on it. If it's just slightly wrong, I'll just leave it alone. Okay, so next part is so that is solid waste characterization. What we're going to do today is kind of a continuing on of what we learned about last week, which is about recycling. So today what we're going to cover in the lecture is about mechanical treatment. Mechanical treatment just means when we treat the solid waste mechanically, we're just sorting and dividing and separating. So we're not burning yet. We'll learn about mechanical treatment. What I'm going to show you is a 20-minute video, which is a video that I prepared when we first had the MCO last year. So it was my first ever online video that I prepared for online teaching. So it's a bit, beginner level, but I didn't. I thought I would just share it with you this time because otherwise I'll be saying the same thing. So watch that and take notes. I'm also going to. I actually already posted in the classroom the slides that I use, the handouts that I use inside the video. So basically, the video is just going through the presentation, some presentation slides. And those notes are already available in your classroom, so you can already download them or annotate them in your own copy. And after I watch, this video is about 20 minutes. After the 20 minutes, we'll take a break. So the break will be, so 20 minutes from now will be about 3:10. So we'll meet at 3:20, 3:10, 3:25. That is 15 minutes, right? So we'll take a 15-minute break. So 3:25, we'll regroup and I'll give you some questions. I have 5 questions. It's kind of a quiz, but it's not graded. But this just to test about what you understood about the video, and then just to reinforce what you're learning. Okay, mana ya? Let me just find that video first. I will share my screen. Make sure that you let me know if you do not hear anything. Saya tak boleh lah pula. Sekejap. Okay. Welcome to lecture 6. Lecture 2. Come. Yep. I'm trying to figure out how to share the screen. Here, lectures. Nope. Okay, can you see a screen that shows mechanical treatment?
Yes, doctor.
Can.
Yes,
Okay.
doctor.
Your learning Welcome to lecture 6. Your learning outcomes are first to be able to describe mechanisms of size reduction, number 2, separation, and number 3, compaction of solid waste. Mechanical treatment is the dominant process at transfer stations and in what we typically refer to as a materials recovery facility, or MRF. This, for example, is a flow diagram of a facility that recovers paper from general waste. Here you see that the solid waste goes through more than one type of mechanical treatment. So it undergoes a series of size reduction and separation from left to right. As the solid waste enters the facilities, it is first reduced in size and then separated into light and heavy fractions. Heavy goes down, light goes up. Further undergoes separation, reduced in size again, and finally is refined through a couple of additional separation processes before you reach the end of the stream. We call our 3 learning sub-outcomes. This lecture is separated into those 3 based on the 3 treatment types, and we'll first talk about size reduction mechanisms. Now, in order to find the right mechanisms or technology to use to reduce your solid waste, you do need to consider a few factors, such as what are your solid waste properties that you're trying to reduce? Are they more light or more heavy? Are they municipal or construction waste, for example? And also you need to consider what kind of materials or end product you want to end up with. Do you want more paper types? Do you want metals specifically, or do you want general combustible fractions? Here, for example, is a figure that shows the distribution of solid waste after size reduction. And say we're interested in paper, we know we're looking at particles with a range of 0 to 70 millimeters and a median of about 35 millimeter. On the other hand, glass is more distributed narrowly between 0 and 20 millimeter size, while plastic is more broadly distributed across between 10 to about 120 millimeter size. This can guide us in the selection of equipment for the particular end product that we are interested in. Another observation we can make is that the bulk end product has a bimodal distribution. The first mode is primarily inorganic, while the second larger mode is mostly consisting of organic materials. Common technologies for size reduction of solid waste are as listed. We will go through them quickly and draw on the differences and similarities. For any of these technologies, you can find manufacturer videos on YouTube that can help enhance your understanding of how it works. The figure shows you what a hammer mill looks like in profile, and what it is a rotating shaft that carries hammers, and these hammers pounce through your solid waste as it enters from the top onto breaker bars here, and the reduced sized waste leaves through the screen from the bottom. A roll crusher is a variation of a hammer mill, but instead of the waste falling onto the mill to be pounded, you have a shaft that pounds onto the waste that feeds horizontally. This is therefore good for heavier waste as they don't need to be dropped onto the machinery. We have next an impact crusher, which is quite similar to a hammer mill, where you have the shaft and a hammer, but instead of pounding on the waste, this hammer slings and crushes the solid waste onto a plate to break it into small pieces. A shredder works slightly differently, where you have rotating blades that chops through the solid waste. It kind of works like a blender. A cascade mill relies on a rotating drum, so you have this drum over here, and inside these drums are steel balls. Crushing happens from the collision between the solid waste that enters into the drum and the steel balls that are moving inside the walls of the drum. Finally, the jaw crusher works just like your set of teeth. So imagine this was your mouth, and this is food entering, and you just chomp through. We've gone through size reduction and have now come on to the second section, which is mechanisms of solid waste separation. There are multiple more ways to separate your solid waste, and we will go through each of these too. And for the first couple of technologies, screens and air classifiers, we will walk through more than one example of each. The most intuitive mechanism for doing waste separation is to use screens. And while we can have clogging problems due to high moisture content in your solid waste, there are also multiple ways to deal with this using screening aids. The first example of a screen technology is what we call a trauma screen. What it is a rotating screen that causes solid waste inside of it to agitate, allowing finer fraction to separate out and sift through the screen. The second example is an oscillating screen, and what it is like a conveyor belt that moves, and this conveyor belt has holes that allows fine fractions to fall through. At the same time, the belt is agitated, and this agitation causes clogs to be released, and this makes it really useful for screening wet solid waste such as compost. A bucket screen relies on solid waste falling into buckets. So you see these buckets here. So all the fine fractions that fits into the buckets is carried onto one side, whereas the rest that do not fit falls through. A disc screen performs both size reduction and screening. The discs are aligned and they all rotate in order to break up the waste. And at the same time, the spaces in between the discs allow finer fractions to fall through. Lastly is a pressure screen, which relies on the differences in pressure between the inside and the outside of a cylindrical screen. So this is a screen. And because of this pressure differential, finite fractions are forced through. So that was a lot of screens, and now we move on to air classifiers. While screens rely on the differences on your particle size to do separation, an air classifier relies on the relative velocity of your particles as they settle. So more dense particles will fall faster than less dense particles. And this is just due to the terminal velocity. Recall terminal velocity is the velocity that you get when the acceleration is 0. So F equals ma is 0, and this just means the net force acting on your particle is 0, meaning gravitational force going downwards is equivalent to drag force going up. Here, for instance, is a graph that shows the settling velocities for different types of solid waste. This is a cumulative distribution graph. So how you read this graph is, say if you're interested in paper, you know that your settling velocities for paper will range between 2 and 5. None of your paper materials or fractions will fall at a rate lower than 2 meters per second. About 50%, so between 0 and 50% here, will fall at a rate of 2 to 3 meters per second, and the remaining half will fall between 3 to 5 meters per second settling velocity. This is in contrast to steel, which ranges higher, so 10 to say 16. And about half of your steel fractions will fall between 10 to 13 meter per second, or at least that's their settling velocities. And the remaining half would fall at a rate of 13 to 16 meter per second. So in summary, steel falls faster than paper, and this can really help you separate them easily by air classification. Here is another figure, but one that plots velocities against density values. And you will find classes of solid waste components. For example, here you'll find metals with high velocities at higher density values. So high velocity and high density values. Whereas plastics here, for example, foam plastic will have lower densities and lower settling velocity values. Formulas. I will actually skip this as it is quite a straightforward calculation of waste loading rate. And what this is essentially how much waste in kilos that you can pass through an air classifier in an hour, given what you know about its area, cross-section, air velocity that you're using in the equipment, and the density of solid waste in your feed. Classified equipments are specified according to their waste loading rate. So this is an important calculation to do, but it's really just plugging in the numbers. And I will let you work through the example problem on your own. A zigzag clarifier blasts air from the bottom to separate dense to light fraction of solid waste that enters from the top. The settling velocity of the light fraction here is easily overcome by the velocity of the injected air. A rotary air classifier works by rotating air, which causes light particles to fling out. A suction hood uses air pressure differences to create air movement that lifts and separates light particles. The dense fractions stays on the conveyor belt. A cross-current classifier and an airbag classifier, which is in the next slide, work in a very similar way as a zigzag classifier, only the direction of air and waste movements are different. So lots of screens and lots of air clarifiers. I will only quickly run through the remaining separator technologies as I believe the sites are quite self-explanatory. In a ballistic separator, the solid waste is agitated on an inclined surface. So what this does is it results in heavier fractions shifting downwards, whereas the lighter fractions shifting upwards. A magnetic separator uses a magnet to attract ferrous materials from your solid waste. In contrast, an eddy current separator uses an electromagnetic field to induce current inside non-ferrous metals. And what this does is it causes them to produce a magnetic field that is an opposite sign to that of ferrous metals. So what you end up with is an automatic separation due to the repelling forces that occurs because of these contrasting fields. Everything else that are not magnetic then falls in between. Optical sorting uses light absorbance properties of materials, and the signals are used to invoke air jets that ejects your desired fractions on cue. Floatation uses air bubbles injected in water to float and concentrate impurities, and this is mainly used to remove ink from newspapers. Density separation works in a very similar way, but relying mainly on the relative density of the materials being separated. So your lighter fractions will float and your denser fractions will settle at the bottom. This is mainly used on light materials such as plastic. Another density separation technology is the hydrocyclone, and it is very much like an air classifier, but relying on water rather than air as the fluid medium. Last but not least, manual separation is an age-old method that has not lost its utility and relevance. It remains one of the more reliable methods of separation of waste, particularly where labor costs are low. Here are some more calculations, but we'll do this interactively during the class session. Try out the example problem and let me know the answer in the group. The first with the correct answer wins a special prize from me. You'll get it after the MCO ends. We have come to the last third of the lecture, and this is a very short section. We'll be talking about compaction. Why do we compact waste? Well, essentially, it's to reduce space, to reduce transportation requirements due to large volumes that solid waste typically tend to take, and also to increase heat density when solid waste is intended for incineration. Compaction of solid waste occurs in three phases. The first phase is mainly due to air displacement, the second due to deformation, and the third phase is consolidation over a long time, and this final phase causes very minimal compaction. Compaction is achieved by two mechanisms. The first is solid resistance and the second is extrusion molding. Solid resistance is basically forcing solid waste onto a stationary wall, whereas extrusion molding is like solid resistance but batch-wise, and variations exist in the form of the briquette press and the pellet press. And that's it. We're at the end, and hopefully by now you should be able to describe different mechanisms for mechanical treatment of solid waste, specifically in terms of size reduction, separation, and compaction. Thank you for listening. Sorry, I didn't realize I was on mute. Let's resume our class. Goody. The video was a bit fast, I think, now that I'm watching it again. But I tried to slow it down, but it was too slow. It was a bit annoying. But if you want to, you can watch it on your own time again as you are revising for your test or whatever next time. But I do have a few questions that I want to ask you to think about when you're trying to come up with the answer and referring to the notes or the video. So I'm going to post this question on the chat and read it to you. All right. Okay. First question. Which separation, not technology, just the generally, can achieve a higher level of purity using an air classifier and why? So feel free to go back to your notes and the video earlier. Both are in the classroom folder. And I will give you 10 minutes. Is that too long? 5 minutes? How long do you think you need?
10 minutes is okay.
Okay, got it. 10 minutes. So after 10 minutes, we'll discuss the results, the answers. Okay, so anybody wants to venture a guess at the answer?
A.
Why?
Because glass and paper have this different density.
Okay. Therefore,
Therefore, it can easily being separated using a classifier.
okay. But what has density got anything to do with it? Which one are you? Which figure are you referring to, Fazli? Ah, can you repeat again your answer? The first part. Is something about something going down. Okay. 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 Good. Anybody else wants to try and elaborate further?
If it's from your lecture note, the diagram is from the zigzag air classifier, the rotary air classifier. We can see that the heavy materials will go down, and then for the light materials will go up.
Okay. Um. Okay. Good. Okay. Uh, there's something that I'm trying to get at here, but you're not there. I mean, everything else is correct, but we're not getting to the exact term that's controlling why it's easy to separate these two. Why does air? How does air classifier work, and how does that relate to density? So for now, if Chana,
For
if you're talking about gravity, right? If you're talking about density, you're talking about gravity. But why do you need an air classifier to do it if you're just separating based on gravity?
Is it velocity, doctor? Settling velocity?
Yes, it has to do with the settling velocity. So if you refer to the if you refer to the notes on the figure on settling velocity, so air classifier operates on the principle that the dense particle has faster settling velocity. So that's the key word. Nah, maksudnya it's okay for you to try and explain it from a density point of view, but you're not really linking it to the air classification. Good. That's great. So next question, ready? Let's see how easy the next one. Okay. This one is there's no choice. Second question is, what do you think is a better separation mechanism for plastic and paper? Okay, I'll give you 5 minutes because I think you have 5 minutes cukup for this one? Cukup? 5, 10? How many minutes you
Go.
need? 5? 5, yeah?
Five.
5, okay. So it's 3:46. Who's got answers?
I
Why?
think manual separation.
Okay.
Optical
I
sorting,
think
doctor.
forcing, doctor.
Optical
Forcing, doctor.
sorting.
I asked spectroscopy. Okay. But isn't that macam too...
It have UV, doctor.
Manual separation is
Can
better.
detect differences in plastic or and paper.
Ain dengan Jana boleh bertenang sikit kot.
Ni tak ada hadiah tau. Korang je semangat sangat. Tapi semangat bagus. I like that you are all very excited on a Monday afternoon. The day before fasting. Tomorrow might be a bit lembik lah. Last chance to be all out. Okay, one answer that I hear is manual separation. Manual separation, of course, is the best for everything. But it might not be the best for large scale operations unless you have a lot of apa nama ni?
Manpower.
Kerja.
Manpower, sorry. Macam ngantuk sekejap. Optical sorting I think is a bit too costly. For just separating plastic and paper, there must be better solutions because usually you use something like that for if you're separating between different types of plastic, for example, something that requires more more precise separation. Because plastic and paper, what are they best separated by?
Density separation.
Density separation.
Density separation.
Sibuk lah Skandar ni.
Because
It's
of
okay, you guys can. Okay.
because of when the pepper is wet, so it will increase the density. So the pepper will sink and the plastic will float.
Okay. I would tend to agree towards this rather than the more advanced options. Any other solutions?
Thermoplastic.
Any other? Sorry?
Using the thermal principles.
Trauma principle. How does it work? How does the trauma screen work?
The plastic and the paper will be on the conveyor belt where it will going a process of drying. Then it will be separated either using electrostatic. After that, something macam tu lah.
Okay. Trauma yang oscillation tu ke? Sekejap. Okay, let me make sure I'm just refer to your slides. Give me a second. Plastic. Trauma oscillated. Trauma screen. Ni screening, right? If you're doing screening, your particle sizes must be if you're referring to the trauma screen technology, I think your particle must be distinguishable by size because it's screening based on the sizes of the open apertures. So if you look at the particle size distribution here, I don't know if I can share it with you my screen. Kejap. Mana tadi? Here. Okay. So here, if you look at the handout, you have this. You see that paper and plastic kind of overlaps quite a bit, except in the somewhere in midpoint of where plastic is distributed. But most of these are kind of overlapping, paper and plastic. So their particle sizes are not significantly different. If you look at the settling velocity, velocity punya gambar. So if you're referring to this trauma screening, I believe this is separation based on size. So their size, particle size should be significantly different in order for you to separate efficiently. So if you're looking at paper and plastic, here, if you set your certain velocity, if you set your air velocity to be around 5, you'll be separating about 50% of the plastic. So it's not going to be very efficient either. So I believe that separation by density will work best using either a floating or hydrocyclone. Okay, next question. Stop presenting. And this is also a 5-minute question. Discuss at P58. What technology can we use to separate aluminum from other materials? The easiest technology. Of course, we can also use manual. Manual is always a safe, safe answer. Okay, so what's the answer?
Eddy current separator.
So everyone agrees this time? No, nobody wants to.
Yes.
Yes.
How does an eddy current separator work? Why is this the only solution? Okay, how does it work?
Electromagnetic field.
Okay, how does it? Okay, it induces a current inside a non-ferrous metal, and that field repulses the field that is within the metal itself. So it's kind of macam mana dia, it's like you are creating a fake magnet to repel from aluminum, so that repulsion creates separation. Okay, good. Okay. This next one is a bit long. And it is it's at some point in the video earlier, I said that we'll do this in class. So this is about calculating efficiency. Number 4, a magnetic separator is employed at a materials recovery facility for ferrous recovery from municipal solid waste. The feed rate to the separator is 15,000 kilogram per hour. So you're putting in 15,000 kilogram per hour of municipal solid waste into a magnetic separator. The feed contains 3.67 ferrous metal. After 1 hour, a total of 65 kilogram is collected in the product stream. And only 46% of this is actually ferrous. So you run the municipal solid waste through a separator, and then you separate metal. You separate iron, and after you collect it, after 1 hour you stop. You collect this separated iron, and you get 65 kilogram of mass. But actually, not all of it is iron. Of course, you try to separate, some of it is going to be contaminated with other things. It's not like a perfect machine. So what I want you to do is calculate 3 different things. 1 is the recovery, 2 is the purity, and 3 is the efficiency of the unit operation. And all of the formula is as given. So X1 is, tak habis copy, hold on. I think this formula is also in your note. X1 is targeted material fraction in the output stream, that is the iron. X0 is the same but in the input stream. Y1 is a non-targeted material fraction in the output stream, and that's Y1, and Y0 is a non-targeted material fraction in the input stream. So I'll give you 10 minutes, enough, or 15?
10, Doctor.
Okay, 10 minutes. We'll regroup at 4:12. That's at 4. Okay. So what numbers did you get for recovery? What?
3.06%.
That's not the same number I got. Anybody else got another number?
41.41. 41.44%.
No. This is recovery, right? Anyone got
Three point 5.6.
Okay, who is that?
I
Iza.
get 83.
Okay. Iza and Adib.
Yes.
Okay, can either of you volunteer to show the rest of the class how you got the answer?
Iza.
Okay.
Thank you.
So basically the X1 is represent let's see, the X1 is represent targeted material fraction. So from the question it said 3.67% is total ferrous material from overall 1,500. So 3.67% we divide by 100 times by 1,500 to get the targeted material for per hour, which is 55.05 kg per hour.
Correct.
So X naught is 3.67% of 15,000 kilograms for every hour.
Yeah.
Okay. Okay.
Then the X1 is 46. The outcome of the product.
Okay.
So then 46 divided by 55.05 times by 100. We get 83.56.
Okay.
Yes, correct.
Good. So
Same with me.
X1, great. Thank you. Good teamwork there. Purity. What did you get for purity? Anyone else got it's around 70%. Did anybody got around 70% for purity?
70.77%.
Good. Okay, Adib pula. Adib, why don't you explain how you got
Tak
purity?
sampai lagi situ.
Oh, tak sampai lagi situ. So, if we don't find anyone other than Iza, we'll ask Iza again. Anybody got purity of 70.8%?
Doktor bagi saya buat 5 minit jap.
Okay. The rest of you, so make sure your X1 is correctly calculated. So Iza already explained how to calculate X1 earlier. It's actually 46 kilograms. And you'll just have to figure out what is Y1 to be able to get purity.
Doktor dah dapat.
Okay, so why don't you explain how you got Y1?
The X1 is 55.05. So using the formula from the lecture, so 55.05 divided by 55.05 plus with 65, that is the total of what we call waste, minus with 46, then we get the Y1, that is non-targeted materials fraction. So after that we just time with 100.
I don't think that's very clear. Can you try again? Or maybe you can use the whiteboard.
Okay. Yep.
Are you allowed to start a whiteboard or only me?
Saya ni lah, apa ni?
Share
Present.
screen. Boleh?
So boleh nampak ke? So from the formula we use given formula is x1 divided by bracket x1 plus with y1. Now it's 100. Sorry for that. So how to get the y1 is from the 65. That is the total waste that after the output minus with 46. That this one is for the targeted material fraction. So after that we got the 65 minus 6, 19. So from here 55.05 divided by the output of plus x1 and y1, 55.05 plus with plus with 19. So after that time with 100, then we get the 74 ke 3. Like
74.
74. So
I got 70. I got 70.8.
70.8.
17.
So Iza, do you agree with his method?
Salah ke?
I think I'm not sure. So I'm not listening, but the easier way is to get y1 is we just look at the end product, which is the total end product is 65 kg minus the total end product for ferrous, which is 46, and we get 19. Then from that, that is 19 is represent y1. So from that masukkan the calculation dia, since we
Sounds
already have
about
x1.
the same. Sounds about the same. Tapi number wise, the final total is not the same. 55 plus 19, 74. 55 divided by 74. Are you sure the what is x1? What is x1?
Doctor, just now
46.
46.
Doctor.
So it's 46 divided by 46 plus 19.
Oh,
So
46.
46 divided
Okay.
by 65. Okay, so 70.8. So sekarang ni we have x naught is how much? X1 is 46. X naught berapa tadi? The 3.67 times 1,500.
55.05.
Okay. That is 55.05 is x naught. X1 is 46. Y1 is 65 minus 46, 19. So that using x1 and y1 only, we can calculate purity. Purity is just how pure is your separation. Finally, you need to calculate the efficiency. Here, you need x1, x0, y01, and y0. So what is the number you got here? Did you get 82.25, Iza?
Yes.
Okay. Do you wanna, well, I will allow everyone else to try and come up with why not first, and make sure that you can get 82.25. So the answer should be 82.25. We already know x naught is 55.05 kg. Y naught is x1 is 46 kg. Y1 is 19 kg. So all you need to apply, to use that equation, you only need to look for y naught. Y naught. But I'll let you try and figure that out. It's just a matter of applying the equation. So once somebody gets 82.25, we'll present to the class. Don't worry, we have time. I only have one more question after this, and this the next question, no calculation. Final is equation. Get it? So what is why not?
1444.95.
Okay, why not is just the original 1,500 kilogram or minus around 55 kilograms. So if you apply that value to the equation, you should be able to calculate the efficiency. Okay. All right, last question before I let you go for the day is for you to design your own MRF, material recovery facility or MERS. Number 5, design a materials recovery facility for a mixed municipal solid waste that will have as the end product the following materials. You want to be able to separate clear glass, colored glass, aluminium, ferrous metal, and corrugated cardboard. Draw a plan for such a facility with the unit operations clearly labeled. So this is kind of like one of the first few slides that I showed in the video. Just an overall layout of what you have to have in your facility in order to separate out all of these materials. You can put any of the technology that was identified for all kinds of separation inside the video. So I will let you have 10 minutes to come up with your own schematic, and then we'll share a few samples in the class and compare them. Okay. So we'll regroup at 4:43. 4:38, sorry. It's 10 minutes. Okay, I'm gonna call out the quieter ones of you. First, Muaz and Navin, could you share your diagrams? Muaz, Navin, and Azra'i. I think I haven't heard your voices yet today. So let's see what you got. Azra'i, Navin, and Muaz, are you still here? I guess you're not. Azmil?
Yes, sir.
Okay. Can you show us how your materials recovery facility look like?
Basically, I'm using the handwritten. Can also.
You can try and show however what
Manage, sure.
you can take a screenshot and share it,
Alright.
or
Screenshot.
and Ain Fitria.
Yes, doctor, me.
Yes. Can you share your diagram as well?
Siap doktor.
Okay. Lain rasanya Syadatul Ami panjang apa ni? Syadatul Nur Syadatul. I can only see the Syadatul Ami. Syadatul, can you please also share your drawing? No response. So no answers from Syadatul, Azra'i, Navin, and Muaz. Nadia Nasir. Hey, she left the meeting. Okay, possibly problem with the connection. Tak apa, we try with those two first. Ain dengan Azmil.
Me first, doctor. Wait, I will present the screen. So basically, I got from the internet. For firstly, from the mixed municipal solid waste, they are put in the kind of the storage, and then they're doing the procedure, not procedure, the technology that tremor screen, and then they do some the magnetic separation, the separation of such as the aluminium from the other element materials, and then they're doing some not modification, there's doing some the process of the hand sorting line, such as the cardboard, the clear glass, the color glass, and the aluminum as well. So from the cardboard, see that it's called like the baler, not baler, I'm not sure, the baler, and then the clear glass and the color glass, they're from the crusher, and the aluminum from the can flattener, and then I think that's all. And then to the is this the
So,
correct?
so, so you're using manual separation
Yeah,
and magnetic separation
yeah,
mainly.
yep.
Okay. Thank you.
Right,
You
thank
can
you.
stop sharing. And did you manage to get everything? Okay, stop sharing and let's hear from Aina. Oh, and she left the meeting as well. Problem internet.
Dia tertekan doktor.
Oh, kesian dia. Takut sangat. But we wait, and then after she presents, we can have a bit more discussion. Maybe any one of you are dying to share your own diagram. We can do that as well. Ain, are you back? There you are. Okay, go ahead.
Okay. Doctor, but I only managed to do this plan. First, we go.
Can you zoom in?
First, we go to dumping, and then we break it and store it, and then go with the primary shading, which we use hammer mill, and then we go to primary air classifier, which we use the drop test, and then for secondary shading, I not able to decide yet, and then go to the secondary air classifier, which is eddy current separator, and the last one is tertiary air classifier. Also, I not decide yet.
Tapi your eddy current separator is not an air classifier, so it doesn't fall under. It's eddy current it uses eddy current separation. Air classifier uses air. This is eddy current separation uses eddy current.
Okay.
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 Okay. Anybody got a good one? Come on.
Come on.
No, that was a good one as well. Good try. Anybody got something that they're dying to share? Come on.
Iskandar want to share something, doctor.
Iskandar always.
Iskandar, doctor. Iskandar. Come on, Iskandar.
Iskandar
You
is very
always
popular
pick our
among the
name.
girls.
No, I'm
Dia kan selalu pick nama orang. Sekarang kita pula pick nama dia.
Cari gaduh. Iskandar, you got voted, so I have to call you to the stage.
How can I share this?
Dapat Iskandar.
I'm using my iPad, so I cannot share it through the.
No excuses. You can always figure out something to share.
I just read it from here lah kot.
Macam mana?
Okay. I just read it.
Tipu, boleh je share.
Screenshot lah. Iskandar patut hantar kat WhatsApp.
Come on lah, MPP.
Come on lah, MPP.
Ya Allah.
Come on, Iskandar. Come on.
Come on, leader. Kata leader.
Who said? Okay, can you see my screen here? Yeah, I changed to Mac.
Bicep dah besar. Come on lah, Iskandar.
Nampak tak?
I can see just your face. Cannot see your iPad.
Okay.
Nampak
this
Iskandar
one.
je.
So first it starts from dumping, alright? So it's go breakdowns to storage, then go screening. Screening we use the particle size distribution, and then we separate it into we separate into two, okay? Cardboard using float sting, alright, and then glass. Then after that, from the same line going to the magnetic and eddy current, and then going to X-ray to separate the colorless and clear one.
Okay, so you separate the paper first, yeah? You separate the paper first, and then
there's light material.
And then you have glass, which you separate using eddy current separator. Okay, make sense? Okay. So you separate paper away, and then that leaves you with glass, colored and clear, aluminum, ferrous metal, and okay, that looks good. That looks good. Anybody else has a different configuration?
Arman want to try.
But you said just now you were using particle density separator. Wait, particle distribution separator. You use air settling ke apa dia? What technology do you use to separate a paper?
Wait
You got 1 minute.
Airbag classifier, Doctor.
Air what?
Airbag classifier.
Okay. Okay, good. So actually, there's no single way to do it. Manual pun okay. It doesn't matter as long as you can separate out what needs to be separated out. But of course, manual is more labor intensive. If you can afford the technology, you do the technology. That means you can increase the flow through your facility. But I hope that you've learned a bit more about the processes for mechanically sorting and separating, as well as changing the properties of your solid waste. I cannot think of any location yet where this will be applied in the future, but most of these processes are happening in the earlier stream of the solid waste processing. Okay, we are at 4:50. It's a good time to go. I wish you all happy Ramadan, inshallah. Have a blessed one. Thank you and see you next week. So hopefully you'll still be as excited as you were today.
Okay,
Bye-bye.
Doctor. Bye-bye.
Bye.
Sure. Okay, bye.
Doctor,
Happy Ramadan,
so for this question, we have a specific answer or it depends?
No, it doesn't have to. There's no single way to do it, but there's always like some. There may be, you cannot say, for example, if you haven't separated out the glass from others, you cannot really use the optical or X-ray separation. So the way you arrange the sequence matters, but I cannot possibly look at in your individual schematic. As long as it makes logical sense from a separation point of view, it is fine. So there's no single way to do it. But of course, it's all first of all, it's objective oriented, what you want to get out of it, and then you have to make sure that the sequence is correct. You cannot you cannot take out aluminum using magnetic separator first and then try to rescue aluminum at the end, for example. So that's there's always the whole scheme of things needs to make sense. Okay?
Okay, Doctor.
Alright, I let you go. Bye.
Thank you, Doctor.
Bye. Thank you, Doctor. Happy Ramadan, Doctor.
Happy Ramadan.
Thank you, Doctor.
Selamat berpuasa, Doktor.
You too. You too.
Thank you, Doctor.
Assalamualaikum.
Salam.
Siapa yang panggil aku tadi?
Doktor record. Dah.
Okay,
Lain, Google Live. Bye. Selamat berpuasa.
Happy Ramadan, guys. Bye.
Bye. Jangan lupa beli sambal hitam. Bye.
Nanti kita ampas rendang kat college. Bye.
Wajib Iskandar.